Hello everyone, today we will be implementing a trie. If you don't already know what a trie is, it's essentially a prefix tree. And what's useful about a trie is it allows you to store a lot of words in a tree structure very efficiently. So in this problem we want to implement a trie that allows you to insert, search, and have starts with methods. And they also tell us that all our inputs consist of lowercase letters A to Z, so we only have 26 characters to worry about, and that all inputs are guaranteed to be non-empty strings. Now, the first thing we want to do when we implement a tree-like structure is worry about the node class and what properties of the nodes and its children. So we will first do that by creating a private class inside the trie class called node. And once we create this node class, we want to give it several properties. So the first thing is that all nodes have children. So we want to create a node array because you can have more than 2 children, so you can't just do left and right. So you have to do an array of children. And we know that the length of this array is 26 because there's potentially 26 different children. So essentially what we're doing here is we're identifying different potential lowercase letters by their index from 0 to 25. And another thing we want to do is because this is a trie, we need to figure out when the word actually stops. So if I iterated down the trie, let's say I had a trie that was something like this, right, for apple. And what if the trie was actually apples with an S, right? But then we know that when I search for apple, this should actually return false. Or the same thing with app, right? App isn't inside this tree, but apples is inside this tree. So we want to create a distinction. So one way we can do this is inside the node class is track the last character for every word. So in our case, if we have the word apple, the last character of apple is E. So this node, we would want to say that it is the end of the word. So we can create a boolean to keep track of this. And we don't need to worry about the constructor because by default, all the entries inside this node array are null, and n-word by default is false. And this is exactly what we want because then all we know that if n-word is true, we manually set it to true, and this is the end of a word. And if one of the children is non-null, then that children exists. Now we should fill out the constructor for our trie class. And this just consists of the root node. And we initiate this root node. Now we can move on to our insert class. So the insert class is essentially iterating down the tree, and when you reach a character that isn't in this trie, then you want to add it. For example, if our tree first has something like AP, right, as the tree, and we want to insert apples, then we first check that A is in the tree, and then we move down to P, and P is in the tree. So now we want to find the next P. And in P's children, all of the children are null. So we want to add P to the children of this P node. And after this P node, we want to add an L node, and then an E node. And this will give us a trie that contains the word apple. So now, how do we implement this? Well, first we want to create a temp node called, let's just call it node, right? And we want to start at the root. And then once we are done with this, we want to iterate through all the characters in the word that we're given. So one way we can do this is because we aren't worried about the index of the word, we just want to get the character, we can use for each loop and iterate through all the characters. So you can call to car array And then now we want to check if the tree already contains this character. So what we do is if node.children and then the character. And here we want to note that all the characters A to Z have an offset of the character A. So we're treating as the characters as integers. And we want to check if this is null, which means that it isn't a child node in the current node. And if it isn't, then we want to add this node. So then node.children say equals to a new node. And we want to create this node. And then once we do this, we want to move to the next character. And at the same time, we want to update our pointer of node to the child node. So we would do this by calling node.children one last time. And once we are done with this, once we iterate through the whole for loop, we know that the node element is at the last element or the last character in the word. So then what we want to do now is set this node and its end word to true. And this signifies that this character was indeed the last character to the word. So once we're done with insert, now we can search for a word inside the trie. And similarly, we want a pointer node that allows us to traverse this tree. And then once we do that, we want to also iterate through each character in the word sequentially. So we also use another for loop here. And then here, we do something similar to what we did in insert, which was using the property that if the child doesn't exist, it is null. So this is exactly what we want to do for search. So if the child is null, then we want to return false, because this means that this word doesn't exist in the trie. And if it does exist, it will just keep on continuing. And we want to just continually update the pointer to the node. And then once we are done iterating through every element of this word, now we want to check if our node element, which is now pointing to the last element, last character of word, we want to check if this is indeed the last element of a potential word that we're looking for. So that's why we return node.endWord. And as you can guess, starts with, it probably has a very similar structure to search. And this is true. So basically, essentially, instead of returning node.endWord, we just return node.true. So we can just copy paste this whole segment into the starts with class and just return true. And so yeah, this is probably how you implement a trie. And let's see if our code works. So line 33, here we want to fix word to prefix because the parameter is called prefix. And if we run it again, we see that the output matches. So now let's submit and see if our code runs. Yep, it's accepted. So we can also have ON log time, which is pretty good performance, and it's probably the best performance you can get because you have to iterate through every character in the word anyways to check if the word is in the tree. Like the video, subscribe, and stay tuned for more videos. Thank you.